Good morning, everyone. My name is Yishan Jiang. I'm a PhD student of AI department at Chunnan National University. Today, I'm going to present my research on end-to-end prediction of cognitive progression in Parkinson's disease using clinical features and DAT spectral images. Parkinson's disease is a long-term condition that mainly affects the central nervous system, impacting both movement and non-movement functions. It's the second most common neurodegenerative disorder after Alzheimer's disease. There is currently no cure, and treatments like dopamine agonists and deeper brain stimulation only relieve symptoms. Therefore, predicting Parkinson's disease progression is vital for personalized patient care. There are many data sets on Parkinson's disease. Uh, PPM, PPMI is one of the most well-known data sets. PPMI offers a comprehensive collection of clinical imaging and biological data, along with processed images and biospecimen analysis results. For neuroimaging, it includes CT, MRI, PET, SPECT, and DTI images from baseline to follow-ups. SPECT is the most common imaging technique in PPMI. The original dimensions of DIT SPECT images in the dataset are 91 multiplied by 109 multiplied by 91. Here are two slides of spectral images, one from a Parkinson's disease patient and one from a health control. Studies show that reduced DIT density in the cardiac nucleus and lower DIT availability in the abdomen can predict cognitive decline in patients. We can also see a significant left-right asymmetry in the patient's imaging. Therefore, we can use the stratum region as the input. Many studies have combined clinical features with spectral images to better predict Parkinson's disease progression. The first paper used a CNN-based method to predict the UPDRS3 scores with longitudinal DIT spectral images and clinical data. The results showed that including DIT spectral images significantly improve the prediction accuracy over using clinical scores alone. Similarly, the second paper found that combining top imaging features with baseline UPDRS3 scores greatly improved accuracy in predicting UPDRS3 scores at year 4. Clinical features and neuroimaging can effectively predict future motor scores. The third, fourth, and fifth papers predict future motor scores. This study had limitations, such as not using deep learning methods or multimodal data for predicting cognitive progression. We aim to develop an end-to-end deep learning model that combines baseline clinical features with spectral images to simplify the prediction process and improve the accuracy. We proposed an end-to-end CM-based model that utilized clinical features and spectral images to predict the cognitive progression for Parkinson's disease patients and health controls. The main contributions of this study are as follows. First, Our model is end-to-end and does not require complex pre-processing of spectral images. We predict the 4-year outcome and include both Parkinson's patients and health controls in the dataset. Uh, we predict cognitive progression based on multimodal data combining clinical features and spectral features, spectral images, which achieves high accuracy. We analyze data from 444 Parkinson's disease patients and 157 health controls from the PPMI dataset. Our participants were enrolled between July 2010 and May 2023. We classified them based on their mental cognitive assessment scores 4 years later. Scores above 26 were normal and scores below 26 were abnormal. All health controls started with more scores above 26, but some had lower scores after 4 years. So we also include them. In the end, we had 164 participants with abnormal scores and 437 with normal scores. We used three demographic and 10 clinical features that previous research has shown to be linked to mock scores in the 4th year. For our end-to-end model, we did minimal pre-processing on the spectral images. We checked their orientation for consistency, normalized the intensity, and cropped them to 34 multiplied by 46 multiplied by 28 for the model input. Figure 1 is the proposed model. The end-to-end model consists of three main components: a clinical module, a 3D CNN module, and a fusion module. We process the clinical features using a simple feed-forward network. We start with batch normalization of the 30 features, followed by two fully connected layers. After each batch normalization and fully connected layer, we apply the leaky value activation functions. The 3D module has three 3D convolutional layers, each followed by value and batch normalization. Max pooling was used after each convolutional block to reduce the size of the spatial dimensions. The resulting feature maps were flattened and passed through a fully connected layer. Then we used the multimodal fusion module that integrated the outputs from both modules. We concatenated the clinical features and the spectral image features. Those were normalized and passed through two fully connected layers. And to avoid overfitting, we applied a 30% dropout after the second fully connected layer. The final step was a sigmoid function to produce the binary classification output. We split the data into two parts. 85% of data for file for the cross-validation to pick the best model based on the highest F1 scores, and the remaining 15 for the testing. Besides our main model, we built 3 other models to compare results. One using only demographic, one use only the 30 features, and one using only the SPECT images. These simpler models did not include the concatenation and 2 fully connected layers from the fusion module, but kept the dropout, final fully connection, final fully connected layer, and sigmoid function. Table 2 shows the prediction results of the 4 models. The models using only demographic data or spectral images did not perform well. The multimodal was the best, with a mean accuracy of 81% and an F1 scores of 0.88. Adding clinical features slightly improved the accuracy. Models using only only use clinical features did not perform as well as the model, uh, which underlined the importance of the clinical features for accurate predictions. Figure 2 shows how well different models predict cognitive progression using the AUC to measure each model's ability to distinguish between 2 classes. Like the results in Table 2, adding clinical features or SPECT images boosted the AUC values. The SPECT-only model had the lowest AUC, suggesting that while SPECT images uh, are helpful, they are not enough on their own for accurate predictions. The multimodal model was the best, with an AUC of 0.84. Although the CNN can extract some useful information from SPECT images, this information is less effective compared to clinical features. Future uh, future research should focus on identifying more useful features from SPECT images. Uh, The MoCA score alone might not fully capture Parkinson progression, including motor metrics like the MDS-UPDRS-3 score would help assess disease progression more accurately. In this study, we only use the baseline data. Incorporating this data to evaluate the future non-motor progression would also be valuable for research. Conclusion: in this study, we developed an end-to-end multimodal prediction model with using baseline clinical features and DIT spectral images to predict the cognitive status 4 years later. Our 3D CNN-based model did not need special pre-processing for the spectral images. The clinical data includes 30 features, with 3 being demographic variables. We compared the performance of different input types, and the results showed that adding DIT spectral images or clinical features significantly improve prediction performance compared to using just one type of inputs. Thank you.